Thank you very much for the introduction. It's a great pleasure to be here, and of course, I would like to thank the organizers for this opportunity. Yeah, as the title says, I will speak about some result concerning singular perturbation problem in systems. So the problem I will be interested in is the following. We consider system of this form where you have three densities, U1, U2, U3, and the equation for the density Ui is Laplacian of Ui equal to beta Ui times the product of the other components to the square. And in principle, you can put some other nonlinear term Fi of Ui. Here you don't see the other components. For the sake of simplicity, I will immediately erase it after this slide. It is not so relevant. Actually, it's not that you can take any function, but you have quite a bit of freedom. And as a boundary condition, you can fix the boundary condition. Ui is equal to some non-negative functions on the boundary, and the boundary conditions satisfy this partial segregation condition. Okay, in principle, you can prescribe this condition only on the boundary, of course, but it is convenient to have it also in the interior. What does this condition mean? This means that the three densities cannot be positive at the same point, the three of them, okay? So for instance, this is an admissible picture for the boundary conditions, okay? You have the blue one, let's say U1, which is positive here, the green one, let's say U2, which is positive here, and the red one, U3, which is positive on this part of the circle. You see, the positivity sets of different components can overlap, but just pairwise. Here you have a picture where you have a triple intersection, and this is not admissible. As I said, here you could ask this only on the boundary, and then you find an extension inside, but it is convenient to have these functions defined everywhere in a minute. We will be interested in the asymptotic behavior of this problem when beta tends to plus infinity. The idea is that this term here in front of this product is responsible for the interaction between all the densities, and beta represents the strength of the interaction. So the larger beta, the stronger the three functions are. Okay, so I will come back. Of course, the first question is, why should one be interested in this kind of problem? So I will come back in a minute at this question. Let me just very quickly make some basic remarks in order to understand the philosophy of the problem. Okay, as I said, let's say that for simplicity, we erase this nonlinear term. And then for every positive beta, we can find a solution of the problem as a minimizer of an associated function. Here is not, the existence is not really an issue. I mean, this function is bounded from below, coercive, weakly lower semi-continuous. So direct methods gives you a minimizer. And okay, of course, at this point, we want, as I said, the idea is to study the behavior of the minimizers when beta is large. So the first observation is that you can easily find some energy bounds for the minimizers. Okay, you just take as a competitor the boundary condition, which I extended also inside. Okay? And remember, the boundary conditions satisfy the partial segregation conditions, which means that the three of them are not positive at the same point, okay? And this means that this term here, the interaction term for this phi is equal to 0. You just have the Dirichlet energy, okay? So here you have a uniform bound independent on beta, okay? Because here you don't see beta anymore. And this gives, of course, a uniform bound for the Dirichlet energy. So up to a subsequence, you can pass to the limit at least weakly in H1. And you also have a uniform bound for the interaction term, okay, for the term which is responsible for the interaction of the three components, which is this product term. So now, if beta is tending to plus infinity, this integral, this term here is bounded. The only possibility is that in the limit also your densities satisfy the partial segregation condition. Okay, in the limit, the three densities, their positivity set can overlap, but just pairwise. Okay. So as I said, you see, you can imagine that this term here is a competition term, saying that penalizing the simultaneous presence of all the three densities in some region. And of course, the larger beta, the more you are penalizing this presence. And in the limit, it is not possible that three densities are positive at the same point by this simple computation. And of course, I mean, at least formally, you can say, okay, we have a sequence of minimizer, you have a singular limit, and you get some limit problem, okay? As I said, at least formally, because we did not prove that the limit is a minimizer. Okay, but the idea is there. And of course, this is the starting point of the investigation, because the natural question are, okay, can we characterize, okay, first of all, can we really see that the limit, the weak limit of a sequence of minimizer is a minimizer of a limit problem? Can we improve the convergence? So far I spoke about weak H1 convergence, which is very poor, but of course one would like to get something more. And of course, what is the regularity of the limit densities, okay? And what is the regularity and the geometry of the emerging free boundary problems? Because in the end, you have these three regions which cannot be positive in the full domain, okay? So some free boundary will appear, the boundary of the positivity sets of each component, and one would like to study the structure of this free boundary. These are the three questions we will be interested in. Coming back to the motivation, okay, this kind of study falls in the larger class of studies, singular perturbation for elliptic systems. Okay, in general, this kind of problem was investigated in the literature for reasons coming both from pure and applied mathematics. The general picture is the following: you have a given number of densities, and the equation for each densities is ruled by diffusion, self-interaction, and mutual interaction, okay, the interaction between the densities. Li are diffusion operators. Typically, one can, in our talk, this will be the Laplacian, but you can take, of course, other diffusion operators. Then, as I said, this is a self-interaction term, nonlinearity, which in reaction diffusion systems, these are called the reaction terms. They are responsible for the self-interaction features of the single density UI. And then you have this term here, Gi of U, which describes the interaction between the different components. For us, interaction will always mean competition, but in principle, for instance, in problem coming from biology, you can have also cooperation, competition, and more complicated pictures. Of course, this system here is let's say, too general to be studied, but there are several studies by now focused in particular on these two classes of interaction terms. Okay, you can have a term like this, where you have some j different from ui uj square. This system is nice because it's variational. It has variational structure, and it comes out both in quantum mechanics, phase separation in systems of Schrödinger equations, but it can be used also as an approach via singular perturbation to optimal partition problems for the eigenvalues, or for modeling harmonic maps into a singular target. So there were many studies with this interaction term. Another interaction term which was quite popular is this term here, where you have some j different from ui uj. This is no more variational, so variational methods here are useless, but the interaction is somehow symmetric. You see, if you subtract the equation for ui and the equation for uj, the corresponding term disappear. And this is the typical interaction terms appearing in population dynamics, Lotka-Volterra type systems. Okay. So just as a quick review on the known results, let me focus for a moment on this kind of problems, so singular perturbation problem, where here, as I said, we choose this interaction term. The sum j different from I of ui uj squared. Remember that in our case, instead, there will be the product, which changes quite everything. But let me review what is known if you put here the sum. Okay. So once again, okay, I neglect the reaction term for simplicity, and I fix some boundary condition. This time I impose the total segregation condition, phi I times phi j equal to 0 everywhere for every I different from j. This means that in this case, the boundary condition, the positivity sets of boundary conditions are really disjoint. Okay? They cannot overlap, not even pairwise. And you can make exactly the same argument I did before. Okay, you find a solution of the problem by minimizing an associated functional. You have uniform bound independently on beta, so you can take the limit. Okay, you have the minimizers weakly converge to some limit, and you have this uniform bound for the interaction terms, which says that the limit densities are segregated. Okay, this times you have ui times uj in the limit equal to 0 everywhere for every I different from j. So you have a total segregation model. And you have exactly the same questions we did before. Can we characterize the limit as a minimizer of a limit problem? Can we improve the convergence? And what is the regularity of the densities and the regularity of the free bound? And by now, I would say the problem is by now quite well understood. It started in the early 2000s. And so this is the picture. First of all, you don't have just uniform bounds in H1, which allows to pass to weak H1 convergence, but actually the sequence U beta is uniformly bounded in C0 alpha log. So you have Hölder bounds for every alpha between 0 and 1. Okay. Up to a subsequence, then by Ascoli-Alzela, you can pass to the limit in C0 alpha log, and you also have strong limit in H1, so not just weak. The limit density is Lipschitz continuous, which is the optimal regularity in, let's say, Hölder spaces, and is in fact a minimizer of a limit problem. And the extremality conditions are the following. Each component of the limit is harmonic where it is positive, and of course you have the total segregation condition. So this total segregation condition somehow it is what gives you a free boundary problem, but it is also what, in principle, you may think, okay, in the limit, the densities are segregated, so I cannot have any information of their interaction anymore, okay, because they don't see each other. But what keeps track of the interaction is this formula here, which is a kind of domain variation formula, or if you are more a PD guy, is a local Porozhaev identity, where you see this is a relation involving all the densities. Here you have the sum of the densities. Okay. And this is not evident, but this is really the key in order to study the regularity of the free boundary. Because, okay, first of all, how we define the free boundary? There are at least two ways. First of all, you can define the nodal set, let's say, the set where every component is equal to 0. Okay? And you can define the free boundary as the union of the boundaries of the positivity sets. It is not obvious at all, but as a consequence of the local Porozhaev identity, you have some kind of unique continuation, which tells you that these two sets must coincide. And so let's say we can focus on one of them. You have the free boundary is a collection of smooth hypersurfaces up to a singular set of Hausdorff dimension at most n-2, and this is optimal. Around singularities, you don't have cusps, but you have just corners, so the free boundary is Lipschitz, and in dimension 2, you have even more results. Moreover, on the regular part, you have a matching of the gradients, so you have a kind of a reflection load. So this is the picture. Okay, in the limit, your domain will split into some in a partition. Let's say in a partition. In each subregion, you have just one component which is positive. The set where all the components are equal to 0, which is the black set here, you see as dimension n minus 1. So you do not have fat region where all the densities are vanishing. And if you take a regular portion, so a regular portion is a portion where, let's say you fix a point and in a neighborhood of this point, you just see two components. In a regular portion, the picture is like that. You have the two densities are actually the positive and the negative part of a harmonic function. Okay, so you have a matching. This is the matching of the gradients. If you take one component and you say, okay, let's change sign, you get something which is smooth. This is the reflection law, which is actually what gives the regularity of the regular part. This is more or less the picture. There are also by now further results regarding fine structures of the singular set or the free boundary up to the fixed boundary. So by now the picture is quite complete. And let me mention, so far, as I said, for simplicity, I say let's take f equal to 0. So in principle, you can take f, which does not allow the existence of minimizers, but it doesn't matter. For the total segregation model, by now is known that you have the very same results also for non-minimal solutions. As a remark, it turns out that the free boundary has exactly the same structure from the qualitative point of view of the nodal set of solutions to linear equations. Okay? And actually, the strategy is very similar because the local Podojаev identity is related to an Algren's frequency formula, which is the key ingredient to study the structure of the nodal sets. And there is also a kind of miracle that you have exactly the same results, but of course you have to change completely the proofs. You have exactly the same results for limits of system with what I call the Lotka-Volterra symmetric interaction. I say this is a miracle because this is non-variational anymore. So in principle, these are really two different problems. It turns out that you have exactly the same structure. So as I said, this is the picture for total segregation problems. Okay, and let me mention that there are, of course, several possible generalizations which are investigated. For all these problems, the picture is not complete, so there are still some open questions to address. Of course, a possible extension is to consider systems where you consider different diffusion operators, for instance, non-local. You replace the Laplacian with the fractional Laplacian. A problem which I really like, but it's super hard, at least for us, is a problem with non-local competition. When you replace a term of type ui uj square, you replace it with ui times the integral over a ball center in x of uj square. Okay, so in this way you are saying the presence of the population ui in a point x is affecting the presence of the other population in a full neighborhood of x. And it's also possible to study systems where each density has its own diffusion operators. This is also quite hard. We just have a partial result of that. But in any case, all these problems are characterized by the fact that the interaction term yields total segregation. Here, in all these terms, in all these problems, you have the sum ui uj square, the sum ui uj, which is what tells in the limit different densities must have disjoint positivity sets. So regarding, so this is different from the models the model we are considering, the model yielding partial segregation, where we say, okay, different densities do not have necessarily disjoint positivity sets. Positivity sets can overlap, but just pairwise. Okay. And regarding partial segregation models, there were really not much. There is one result by Caffarelli and Roquejoffre in the 2008. They studied uniform Hölder bounds for some exponent. Okay, the exponent is unknown, of solution of this system here, which, if you want, is the natural generalization of the Lotka-Volterra system in a partial segregation setting. So you say Laplacian of Ui is equal to singular perturbation parameter beta times the product of all the densities. And for this system, just a remark, of course, it doesn't have variational structure, but the key feature is that the Laplacian of Ui is equal to the Laplacian of Uj. Okay, so if you subtract, you obtain a harmonic function. And so it's like to have some kind of vector valued harmonic. It's like to take the maximum of a bunch of harmonic functions and to study the properties of this maximum. So here you have uniform bounds. There is also this very recent paper where the authors established some properties of the limit problems, uniqueness, optimal regularity of the solution, which is actually Lipschitz regularity, and then they do some examples and numerics. But the free boundary problem, for instance, here is open. So this is all what was known regarding partial segregation problems, and this was somehow our motivation to start the investigation. Okay. So we started the investigation. They considered the generalization of the Lotka-Volterra system. We considered the generalization of the system with variational interaction. So we consider to start, let's take everything simple. We want to minimize this functional here and to study the asymptotic behavior of minimizers when beta tends to plus infinity. Okay, so this is the first result we have. The first result concerns Hölder bounds. Okay, we have already observed that for every beta you find a minimizer, you have uniform estimates in H1, which leads weak H1 convergence. Our first result concerns the validity of uniform estimates in Hölder space. Okay, so there exists an alpha bar between 0 and 1, such that you have Hölder bounds up to this alpha bar. Okay, you have Hölder bounds in C0 alpha for every alpha smaller than alpha bar. So let me point out that this alpha bar is smaller than 1, so we don't have uniform bounds for every alpha, but up to some thresholds. Okay, we have uniform bounds for small exponents, let's say. This, in any case, is sufficient to pass to the limit in C0 alpha log, actually. You also have a strong limit in H1, and you get a partially segregated configuration in the limit. Moreover, it's also not difficult to prove that the limit is a minimizer of a limit problem, the natural limit problem. I would like to make some remark about this theorem, especially to the role of alpha bar. Okay, but before, let me just say that the previous theorem is enough to get the extremality condition satisfied by the limit. In the limit, you have that each density is harmonic where it is positive, and you have, of course, the partial segregation condition. Moreover, from the variational interaction, we also recover a domain variation formula, okay, which was, as I said, this was the key ingredient in order to study total segregation models. So this is a good news. We have the domain variation formula. So at this point, before proceeding, one may say, okay, let's try to understand the behavior of the function satisfying this extremality condition. Okay, let's try to understand the behavior of extremal configuration, and we see that the behavior it can be quite, let's say, funny, especially if you compare it with total segregation model. First of all, you can have this is an admissible extremal configuration. You can have one component, let's say the third component U3, which in the limit is positive everywhere, and the other two satisfies a total segregation model. This is fine because once the two components are satisfying that are totally segregated, the third one can do whatever it wants. Then we can have a picture like that, which is somehow counterintuitive from the point of view of the coming from a limit of minimizers. Okay, you can have two components. Let's say u1 and u2, which are equal to 1 over square root of 2x plus, and the other which is equal to x minus. This does not really seem looks like a minimizer, because you see the partial segregation condition is already paid from the fact that x minus and, let's say, the red component are segregated. Okay, so this means the third component, the green one, could make whatever it wants in order to minimize the energy, and at some point it is not convenient to develop a corner. Okay, it is convenient to stay positive. So this is not really a good candidate to be a minimizer, but it is an extremal configuration, which tells you already that the regularity for extremal configuration, for non-minimal configuration, is different from the regularity of minimizer, which is already a big difference with total segregation models. And also, if you go in higher dimension, you see that you have some very reasonable extremal configuration. I say very reasonable because this is super symmetric. It's quite nice, which is not Lipschitz, it's Hölder. Okay, you can take, this is the prototypical Hölder solution. Let's say in the ball, you split, you put as a boundary condition, you put the sinus of 3 over 4 theta plus, and then you rotate, you just rotate this configuration with an angle of 2 over 3 pi. And in the limit, you can say, okay, I take the 3-4 harmonic extension. So you have this function here. The red one is harmonic in this region of the ball, which is a cone of opening larger than pi. So this function is Hölder, is the harmonic function, which is Hölder continuous and positive in this cone. You just rotate this configuration and you get 3 configurations whose positivity sets are partially overlapping, but just pairwise, so this is fine. This satisfies the partial segregation condition, and the regularity is just C3 over 4. So maybe, of course, here I'm just saying this is an extremal configuration, is a candidate to be a minimizer. This suggests that probably the optimal regularity is below Lipschitz. Okay, it's just Hölder, is very different, once again, from total segregation model. In fact, this will be the case. The last result which I'm going to present is that this is really a minimizer. So this is the optimal regularity. So to come back to the role of this alpha bar, we got Hölder bounds for some small alpha bar. At the beginning, we said, okay, maybe we missed something, but in the end, it's very natural. You cannot have uniform bounds in C0 alpha for every alpha. Otherwise, you would have C0 alpha regularity for every alpha for the minimizers, but this, in the end, will not be the case. At this point, one may say, okay, is it really this alpha bar equal to 3, 4? In our proof, the answer is no. Let me just give a brief sketch of the proof of the result concerning Hölder bounds. This is quite typical. One argue by contradiction and say, okay, let's say that we don't have uniform bounds in C0 alpha, then we make a blow-up analysis. We find a couple of sequences, x beta, y beta, where the Hölder quotient is blowing up. And the idea is to renormalize the sequence around these blow-up points. Okay. You renormalize it in such a way to have these new functions v beta, whose C0 alpha seminorm is precisely equal to 1. Okay. So it's not just bounded by 1, it's exactly 1. This means that these functions v beta have they must oscillate a bit. Exactly, they must have a C0 alpha seminorm equal to 1. Okay, you scale, you see that this V beta satisfies a similar problem, okay? But you have a new let's say, singular perturbation parameter M beta. At this point, Since you already renormalized the C0 alpha semi-norm, you know nothing about m beta. This could go to 0, could go to a positive constant, could go to plus infinity, okay? So, and the idea is to show that for all the possible behaviors of the parameters, there is convergence to some limit problem. And then you want to get a contradiction by means of some Liouville type theorems. Okay? You have noticed that if you have convergence, let's say in some reasonable sense, the limit configuration must have an oscillation of exactly 1, because the C0 alpha semi-norm is equal to 1. Okay? And so what you want to prove is that if alpha is sufficiently small, if the Hölder exponent is sufficiently small, this is not possible because the limit problem only have constant solutions. Okay, this is the idea. This is the idea, and it's quite technical to put everything in details. But in the end, everything boils down to find some Liouville type theorems for this system here. Okay, here you just get a system exactly like our original problem, just that you have the system posed in the whole space, and here you don't have beta, but you have a positive constant. While here, there is another possible limit problem where you have the 3 densities which satisfy the partial segregation condition. They are harmonic when positive and they are subharmonic everywhere. And once again, the problem here is posed in the full space. So one would like to say, okay, if alpha is sufficiently small, these problems only have the constant solutions. Okay? And this can be done. We took inspiration from the results by Conti, Terracini, and Verzini on total segregation models. Can be done by using some Alt-Caffarelli-Friedman monotonicity formula. Here we had to prove an Alt-Caffarelli-Friedman type monotonicity formula where we took not just in the monotonicity formula, you have the product of basically 2 weighted densities, one for one component and the other for another component. Here instead we have a different formula where we take the product of all the components, of course, because we want to keep track of the interaction of all the 3 components at the same time. So it's interesting that one can prove an Alt-Caffarelli-Friedman monotonicity formula for a functional of this form. And this formula is precisely what allows to prove the Liouville type theorems which one needs. I don't enter into the details, but this was just to mention this. About the monotonicity formula, this is what gives exactly the alpha bar, okay? Because exactly like in the original Alt-Caffarelli-Friedman monotonicity formula, okay, you see here we have an exponent which I call the nu. Nu for me, nu bar is the optimal exponent for the Alt-Caffarelli-Friedman monotonicity formula. And this exponent nu bar exactly is in the original paper by Alt-Caffarelli-Friedman, comes from an optimal partition problem. Okay? But this time you have, let's say, an overlapping partition problem. You want to divide the unit sphere into 3 sets, which are not disjoint pairwise, but you just require that the common intersection of the 3 of them is empty. Okay? This nu bar is what gives the optimal exponent in the monotonicity formula and the optimal exponent for the Hölder estimate. What is this optimal exponent? We don't know in principle. We can say that it exists, it's positive. My idea was that the optimal exponent comes from this configuration. So you split the unit circle, for instance, in dimension 2, into 3 equal parts. So 3 angles of 4 over 3 pi, okay? And you can do it in such a way, you arrange them in order to satisfy the partial segregation condition. But in dimension 2, one can make explicit calculation. You know the first eigenvalue of the Laplace-Beltrami on the arcs. On each arc of size 4 over 3 pi, the first eigenvalues is 9 over 16. So you compute exactly this sum here, and you get 9 over 4. which was my candidate to be an optimizer. But instead, it's very easy to find variations decreasing this value. It is convenient that two components are totally segregated. So you split the circle in two, and you say, okay, as one component, as one set, I take this half. As the second set, I put this second half. And at this point, this partial segregation condition is satisfied. So as the third component can be the full circle. And at this point, lambda 1 of the full circle is 0. So this third component does not pay anything. The other component, the first eigenvalue, is 1. And so in the end, you see that by taking this sum for this configuration, you get 2, which is smaller than 9/4. And so this is one way to... So the symmetric solution, which in principle could appear as the natural solution, is not the minimizer. Probably this is a minimizer. We don't know, actually. This was just to say, this is the reason why we could not get uniform bounds up to the exponent 1, and actually not even up to the exponent 3/4, which is the right exponent for the regularity. In any case, we have these uniform bounds for a small exponent. We have the domain variation formula. We can start trying to investigate the regularity of the free boundary problems. Okay, and there are at least two natural ways to define the free boundary. The first way is the following. Okay, we say we take a function satisfying the partial segregation condition, and when so at each point of our domain, we define the multiplicity of this point in this way. The multiplicity is the number of components which are vanishing in that point. Okay? So we have triple points, which are points where all components are vanishing. We have double points, points where two components are vanishing and no more. And we have points of multiplicity 1, points where just one component is vanishing, and point of multiplicity 0. Okay. So point of multiplicity 0, we don't have by the partial segregation condition. At each point in the limit, at least one component must vanish. In point of multiplicity 1, two components of the limit function are positive, and by continuity, they are positive in a full neighborhood. So in a neighborhood of each point of multiplicity 1, you have just one component which is vanishing. So the picture is very clear around that point. So the first natural way to define the free boundary is this one. We take points of multiplicity 2 or 3. Okay? We take the union of these two sets. Another natural notion of free boundary is to take the union of the boundary of the positivity sets of all the components. Okay? For extremal configuration, in general, these two sets are very different. For instance, take this configuration here. Then in this case, the union of points of multiplicity 2 and 3 is the full half line minus infinity 0, because in this half line, two components are vanishing. Okay. While the free boundary is just the origin. So for extremal configuration, in general, these are very different. But in fact, it turns out that for minimizers, they are equal. Okay? The key ingredients for us were the following. We have, I already mentioned, we have the domain variation formula. So one may say, okay, you use the domain variation formula and you study everything like in total segregation models. This actually does not work. The domain variation formula is helpful just to treat triple points, just to treat points where all the components are equal to 0. Otherwise, we did not find any way to use it. And in the end, we were quite convinced that it is natural, that it is completely useless to study double points. To study double points, we really use the minimality. Okay? The minimality tells that if you have one component which is 0 in a ball, and you have another component which is not identically 0 there, then this second component stays positive. Okay? Because in any case, it is sufficient that one component is positive. So minimize the other, once that you have one component which is 0 in a neighborhood, the other components are positive. Then always the minimality tells that if two components are totally segregated, then the third one is harmonic. And moreover, especially super useful is that in points of multiplicity 2, so well, two components are equal to 0 and the other is positive, these points are nodal points of harmonic functions. Okay? If V1 and V2 vanishes at x0 and V3 is positive there, then V1 minus V2 is a harmonic in a neighborhood of that point. So these three ingredients, which comes really from the minimality, is what allows to prove to study double points. Triple points, you use the domain variation formula, as I said, which gives an Algren monotonicity formula. And this tells that the set of triple points has empty interior. You have a jump of the vanishing order at triple points. Okay? If at double points or even at points of multiplicity 1, the limit of the frequency is equal to 0. And instead, at triple points, the limit of the frequency is greater than or equal to the alpha bar given by the theorem about Hölder bounds. And you also have the homogeneous blow-up. Okay, at each triple point, you can make homogeneous blow-up. So combining all this stuff, in the end, one can study the free boundary regularity, which is interesting because we still don't know the optimal regularity of the limits, but in any case, we are able to study the free boundary regularity. First of all, for minimal configuration, we have the two notions of free boundary I introduced coincide. And moreover, the free boundary has dimension n-1, and you have a splitting into regular and singular part. The regular part is the union of smooth hypersurface, as usual, of dimension n-1, and consists only on double points. Okay, so it's the set of double points. So you have that this is basically the nodal set of a harmonic function. While the singular set consists of some double points, the singular double points plus the triple points, and has dimension at most n-2, and actually is discrete in dimension 2. And as I already mentioned, this is completely different for externals configuration. Okay, so still we have to discuss the optimal regularity of the solutions. As I said, at that point, after the considerations we made, we were convinced that the optimal regularity was C0 over 3,4. And in fact, this is the case. This is the case, okay? The way we proved it is the following: is we did not just prove the C0 3,4 regularity of the limit, but we could prove the validity of C0 alpha Hölder bounds for every alpha smaller than 3,4. Okay, which one may say, okay, but before you told me that you proved uniform bounds for C0 alpha only for alpha small, and in fact, by using C0 alpha bounds for alpha small plus some information coming from the regularity of the free boundary, we can improve the estimates. Okay, we can obtain estimates for higher alpha. This is a kind of improvement of regularity. For us, at least, it was not possible to directly prove C0 alpha estimates up to 3/4, but we first needed to show C0 alpha estimates for small alpha, study the free boundary problem, and then use all the information in order to improve these C0 alpha bounds. Okay. And as I said, this is optimal in the sense that you can choose some boundary condition in such a way that the minimizer of the limit problem is a minimizer with regularity C0, 3,4, and no more. How much time do I have? Okay. Okay, 15 minutes, wonderful. So just a word about this theorem about the improvement of the Hölder bounds. The idea was the following. we want to improve the Euler bounds, so we want to improve the Liouville type theorems, okay? And the Liouville type theorems, which I mentioned at the beginning, are valid, are true for every solution of these two problems. Instead, now we really want to use the local minimality. And we want to use the Euler bounds by considering just homogeneous solution, okay? Because the Euler bounds for small exponents allow to make blowdown. You start with a non-constant solution of this, non-constant entire solution of this problem. You make blowdown and you obtain a homogeneous solution, homogeneous locally minimal solution. And at this point, you can focus just on homogeneous solution, and this is the key to improve the Liouville theorem. Okay, to obtain, as I said, to obtain homogeneous solution, one has to make blowdowns. To make blowdowns, we used the Euler estimates. And in dimension 2, the homogeneous problem can be solved explicitly. In higher dimension, one has to make a dimensional reduction, but this is not so easy, but yeah. The minimizer, just a word about the optimal regularity. The minimizer with fixed rays is exactly related to the configuration which I was discussing at the beginning. So you have this profile which looks like the Mercedes star, which is really a minimizer. And okay, this is basically all what we did. I would like to, in the time that remains, I would like to still make some remarks and also comparison on other results. Okay, I was mentioning that the other studies related to partial segregation models were studied by Caffarelli, Roquejoffre, and Burger and collaborators. So what did they prove? They considered this problem. By Caffarelli, Roquejoffre, you have uniform Euler estimates for some exponent. And in fact, the limit densities are Lipschitz. So in this case, they could prove that in the limit problem, you obtain something with Lipschitz continuous densities. So this is completely different from our case where we have C0, 3, 4 maximal regularity. Okay. So as I already emphasized, this kind of partial segregation model seems very different from total segregation models. In total segregation models, you take the Lotka-Volterra interaction, all the variational interaction, in the end you get the very same results. In this case, instead, you get very different results. By the way, this problem, as I said, is completely open from the point of view of free boundary, and I think it's very interesting. Because one can, to understand the type of situation which one has, one may say, okay, let's take as a toy model a one-dimensional problem on a segment. Okay. You take the one-dimensional problem on the interval 0, 1, and you fix this boundary condition. U1, in 0, you have U1 and U3, which are equal to 1, and U2, which is equal to 0. And in the point x equal to 1, you take U1 and U2, which are equal, U2 and U3, which are equal to 1, and U1, which is equal to 0, okay? In this case, one can make really explicit computation, because remember, you take the difference of two densities, and the difference is always harmonic. And this property passes to the limit since you have uniform Euler estimates. So one can solve everything explicitly, and one gets that V1 is like this, the red component. V2 is the blue one, and V3 is this component here. So it is the difference of different components is harmonic, but even if a component remains positive, it is not harmonic in its positivity set. It satisfies an equation with a measure. Okay? Because, this is exactly related to the fact that the Laplacian of all these components are equal. So once that one develops a measure, all the functions must develop a measure. So in this case, for instance, one may be interested in study the free boundary as the sets where the Laplacian develops and measures, and as far as I know, nothing is known. Nothing is known. And as I said, once again, this is very different from our model, because in our model, if you are positive, you are harmonic. Here, this is not true. If you are positive, in any case, you do not satisfy a very nice equation. But probably you can exploit, even in higher dimension, there is some clever way to exploit the fact that you take the difference of two components, and this is harmonic. By the way, also in our problems, there are some interesting questions which remained open. For instance, one thing which I did not mention, okay, we have results for minimizers, for any minimizers. In any case, it is interesting that in general, we don't have uniqueness of minimizers, okay? We can take exactly the same toy model as before. This time we say, okay, let's say that U1 is equal to A in 0, U2 is equal to B in 0, and U3 is equal to 0 in 0. And in the point 1, you have U1, which is equal to A, once again, U2, which is equal to 0, and U3, which is equal to B. Then, okay, a very natural candidate to be a minimizer is this one, where you say, okay, U1 is positive in both extrema of the interval 0, 1, so it's very convenient for U1 to stay constant. There is nothing from the point of view of the gradient, okay? And then the two components satisfies the total segregation condition. This is convenient, this is the minimizer, but just if A is larger than B, or if it is smaller than B, but close. If A is very small, it is convenient to have a different shape. So in general, we have no uniqueness of minimizers. So there is everything here is continuous, so there exists exactly one for every you fix B, and there exists a special value of A, such that for A equal to A bar, you have two minimizers. For instance, this is another extra difficulties of this type of problem, where you don't have uniqueness of minimizers. And okay, maybe I skip this. And here I wanted just to make, to list some open problems. Of course, the first question is, what about non-minimal configurations? We already know that, okay, minimal configurations, we have a good picture. Extremals configuration, we have a very bad picture, but we can take limit solutions coming from non-minimal solutions of the beta problem. These may have some nice regularity with respect to just extremal configuration. So this is a first open problem. Second open problem, we consider three components, because at the beginning we say let's try to keep stuff simple, and this was already complicated. But what about if you put more than three components? If you put more than three components, you have at least two ways to generalize the problem. We are studying this stuff with some PhD students, because you say, okay, partial segregation with k components, we understood it. You may say, okay, this may be that at most k minus 1 components are positive at each point. Okay, but you may also say, okay, I take 4 components and I let them interact 3 by 3. Okay, so I just take on the right hand side of the equation the products u1 u2 square u3 square plus u1 u2 square u4 square plus u1 u3 square u4 square. These are at least two different generalizations, and the optimal regularity should be different in all these problems. Then, of course, okay, I consider a problem like, let's say, related to harmonic maps, where you fix the boundary condition, but at that point, in the same spirit, one may consider partially overlapping partitions. Okay, so partition, you take an optimal partition problem with Laplacian eigenvalues, but you don't prescribe that you really have a partition, you allow a partial overlapping. And okay, and that's all what I wanted to say. For the attention.